Hi, I'm going to talk about kernels in token digraphs. And this is a joint work with Cesar Hernandez Cruz, who is giving the first talk of the conference. Okay, so first of all, what is a token digraph? Well, given a digraph G, we can construct its k-token digraph, defined as follows. The vertices are the set of k vertices of the graph G, and the arrows are of the form AB, where the symmetric difference of A and B is precisely an arrow of G. This means that the symmetric difference is the set XY, where X belongs to A, Y belongs to B, and XY is an arrow of G. The symmetric difference is just taking the union of the sets A and B and then removing their intersection. Okay, so here is an example of a token digraph of this graph here. It's just a cycle with two leaves attached. And this is its token digraph. It's just an example. And I also need to define what is a kernel. So a kernel of a digraph G is a set of vertices N, which is both independent and absorbent. Independent means that there are no edges between vertices of the set N, and absorbent means that for every vertex C outside of the set, there exists a vertex X inside the set, such that there exist the arrows CX in G. And this would be an example of a kernel. If we consider this digraph, the dark blue vertices are a kernel, since there are no edges between them, and there is an arrow for every light blue vertex to one dark blue vertex. And the most known result about kernels states that every digraph without directed cycles of odd length has a kernel. Obviously, it's not an equivalence. I mean, there are digraphs which have odd directed cycles which have a kernel, but if they don't have a directed odd cycle, then we know it definitely has a kernel. And that is a good thing, because when we consider the token digraph of a digraph without cycles of odd length, then we obtain a digraph without cycles of odd length. So here's an example. If we consider this graph here on the left, it does not contain a cycle of odd length. This means it has a kernel. The vertices on the bottom, which are orange, form a kernel for this digraph. So we should have that its token digraph has a kernel. This is its two-token digraph. All my examples will be for k equal to 2, because when k is 3 or larger, the pictures are very large and you cannot see them, visualize them nicely. So here we can see that, again, the orange vertices form a kernel for this digraph. They are the vertices 1, 2, 1, 3, 2, 3, and AB. We can see that there are no edges between them, and they are absorbent. Okay. So one then can ask if this always holds. Is it always true that if G has a kernel, then so does F its token digraph? So to answer that question, we can look at these three graphs. The first one has a kernel. The pink vertices form a kernel for this digraph, and the other two do not have a kernel. I'm going to call them G5, H5, and C5. And then we are going to look at the token digraph of the first one, of G5. It is this graph here. And the answer to the previous question is no. This digraph does not have a kernel. Why? Because it has a strong connected component, which is terminal, and does not have a kernel. So this strongly connected component is isomorphic to the directed cycle on 5 vertices, which does not have a kernel, and there are no outward going arrows that go from here to the other part of the graph. this means that this cannot have a kernel. But what is interesting and really nice about this is that if we reverse one arrow, I mean, if we take the graph we started with and we reverse this edge, if we started with a graph which had a kernel and its token digraph did not have a kernel. We reverse one edge, one arrow, we turn it around, and then we obtain a graph which does not have a kernel, but its token digraph does have a kernel. So this is its token digraph. And as you can see, the orange vertices form a kernel for this digraph. And this is really nice. So our first nice and good result is the following, is that if we have a directed cycle, then its token digraph on any amount of tokens has a kernel. Obviously, if our directed cycle is of even length, then trivially it has a kernel and we are done. So the proof is basically just focused on the case when we have a cycle of odd lengths and when k is larger than 3, because when k equals to 2, it's really easy to see that it always has a kernel. For example, this picture here is the token digraph of the directed cycle on 7 vertices. And then the blue vertices form a kernel for this digraph. And what are the blue vertices? Our vertices, I mean, if we enumerate the vertices of our cycle with the numbers from 1 to 7, then the vertices which are set such that their difference is 1 or 3, that is a set which is a kernel. So for example, we have the vertex 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8. Sorry, this was on 8 vertices, on 9 vertices, not on 7. And I started numbering them with from 0 to 8 instead of 1 to 9, but it's basically the same. And then I also take in the kernel vertices which their difference is 3. So I have 0, 3, 1, 4, 2, 5, 3, 6, 4, 7, 5, 8. This shouldn't be 0, 6, but I have, sorry, and 1, 7, and 2, 8. So if when we have k equals only to 2, it's very easy to identify the kernel. The digraph will always look like this, and you can start by taking the vertices of degree 2 and then completing the kernel, and it always works pretty nicely. So it starts to get complicated when k equals to 3 or more. So in that case, I'm going to give the sketch of the proof. I'm not going to give all the details because I only have 20 minutes and I will take a lot of time. So when k is 3 or more, what we need to do is we need to construct an auxiliary non-directed graph, which I shall call G and K, where the vertices are k tuples with the cyclic ordering, which have as entries integer numbers between 0 and n minus k, such that the sum of their entries is n minus k. And what does this then represent? Why am I taking this cyclic ordering of k tuples? Well, so assume you have a vertex in your token digraph. This means you have a set of k vertices in your cycle, a set of k vertices of your cycle. So imagine you have this here. Then the black vertices correspond to a set of vertices. Assume k equals to 5. I have the cycle of length 13. And then this corresponds to one, or actually to more than one vertices, because this could be the vertex with the label 1, but this could also be the vertex with the label 2, 3, 4, up to 13. So actually I have 13 vertices that look like this. So all these 13 vertices, I'm going to put them together in one vertex of G and K, and representing, I mean, the vertices of G and K are going to represent sets of vertices of the token digraph. And as how am I doing this? Well, the tuple is defined as follows. We take a look at the black vertices, and we're going to count the number of white vertices that are between the black vertices. So for example, between these two black vertices, I have 0 vertices that are white. Between this and the following, I have 1 vertex. Then I have 2, then I have 3, and then I have again 2. So this would be a vertex in my graph G513, would be the vertex 0, 1, 2, 3, 2. Of course, I can name this vertex starting with the 2 and ending with the 0, or starting with a 2 and ending at a 3. It's all the same because I am taking the cyclic ordering. Okay, so these are the vertices of my graph G and K. I also want to define edges between them. The edges, there's going to be an edge between such a vertex and another one if the other configuration of vertices of tokens on my cycle can be obtained from this one by moving only one. So formally, what does this mean? Assume my tuples are x1 up to xk and y1 up to yk. Oh, sorry, this is not my laptop, so I keep pressing things that I shouldn't press, and that's why I keep accidentally turning the page, because my laptop it's not so good for recording. Sorry. Okay, so these two vertices are going to be adjacent if every entry is the same but 2, and those 2 differ by 1. But if one is one more than, if for example xi is yi minus 1, then xi plus 1 must be yi plus 1 plus 1. So they only differ by 2 consecutive entries, which are one is one more, and then the other one should be one less. And then what is interesting about this graph is that this graph can have loops. It is not a simple graph. And the loops are actually very important here. So for example, this vertex has a loop because we have the edge 0, 1, 2, 3, 2 and 1, 0, 2, 3, 2. But in the cyclic ordering, these two are the same vertices. You can turn them turn them around and obtain the same vertex. So this is a vertex with a loop. So an example of how this graph looks like, and actually every time I have k equal to 3, it's going to be a planar graph, but for k larger, not anymore. So my example is for k equal to 3. This is the graph G317. For now, just ignore the colorings. I'm going to talk about that in a few moments. And so we have several loops, several which are not loops, but it's like a triangle with more triangles inside. So in this case, it looks pretty nice. Okay, so why is this graph important? As it turns out, the edges are also like in a correspondence with the arrows of our token digraph. How? Well, as follows. Let's assume AB is an edge in G and K. Oh, again, sorry. Is an edge in G and K. Then for every vertex Y in B, there exist vertices X and C in, sorry, this is, I put B, but I meant to say A, such that there is an arrow from X to Y and from Y to C. This means that every edge in my graph G and K corresponds to arrows in both ways in my token digraph. So I will always have, for any vertex in B, an arrow from a vertex in A to B, and an arrow from that vertex in B to some vertex in A. So I have them in both ways. What else? The vertices which do not have loops correspond to independent sets in my token digraphs. This means that if there are no arrows, no loops in my vertex, that means that there are no arrows between the vertices that correspond to that vertex. And what does this mean? This means that any dominating independent set of vertices in G and K which does not contain any loops leads to a kernel of my token digraph of the cycle. And this is amazing because it is much more easy to obtain a dominating independent set of vertices in a graph which is not directed but only has a few loops than to obtain a kernel in my really large token digraph. Like the example I put for the cycle, this one is pretty large and I'm only taking K2 equal to 2 and the cycle of length 9. So it is small and it still has a lot of vertices. So as you can see, this graph is much smaller. So it's much easier to work with this graph, and that is amazing because this basically solves the problem. Okay, so I'm not going to give the details on how what the dominating independent set is because it requires many cases and I do not have time. But if you want to know, I'm happy to email it to you. So I'm only going to give this example when k equals to 3. In this case, the set of vertices which have a loop are of the form v, v plus 1, and w. Thus, it is enough to have 2 consecutive integers for it to be a loop. And then I'm going to consider the set I, which corresponds to the vertices that are x, x, y, where y is different than x plus or minus 1. Then this is an independent, I is an independent set which dominates the vertices with loops and does not contain any vertex with a loop. By dominating is the same, when it is a non-directed graph, it's the same as absorbing. So just think as absorbing anytime I said dominating. Sorry, I didn't define it. It's just when it's undirected, it's the same. When it's directed, it's the other way around. But here we don't have directions, so it's the same. Okay, so as we can see here, the vertices with loop are precisely those which contain 2 consecutive vertices. So here we have 4, 5, 5, 6, 3, 4, 2, 3, 1, 2, 0, 1, and 6, 7. These are the vertices with a loop. Then my independent set is the vertices which has 2 equal entries. So for example, you have 4, these are the purple vertices. We have 4, 4, 3, 3, 2, 2, 1, 1, 0, 0, 6, 6, and 7, 7. Here we have 5, 5, but this one, it has a loop because it also has 4. So this does not correspond to my independent set. And actually, it is adjacent to one of the other vertices of my set. So we can extend this to a dominating independent set of the whole graph. For example, we only need to add this one, 2, 4, 8, 0, 3, 11, and 0, 5, 9. You can pause the video and check it yourself if you like. And that is an absorbing independent set of this graph. So if we take every vertex which corresponds to the purple vertices and to the other 3 vertices I mentioned, you will obtain a kernel for the token digraph of on 3 tokens for the directed cycle of length 17. And you can do this in general. So that is a really nice theorem, and I think this proof is very beautiful because it involves another graph, which makes everything much simpler, and that's amazing. So one other final result I have, just to finish my talk, is going just one step further. Remember the graph GN I mentioned before? Let me go back. This one right here, which is a directed cycle, and I put just one edge going towards the cycle. This I'm going to call HN, I believe. Perhaps somewhere I wrote down GN, but I meant to say HN. I renamed it by GN, sorry. And so just to give the formal definition, CN the directed cycle, I label the numbers with from 1 to n, and GN will be the digraph, which also contains the vertex 0, and we have the arrow from 0 to 1. Then the theorem that we obtained is that when k equals 2, 3, or 4, then the graph fk of the token graph on k tokens of my graph GN has a kernel. GN is also an orientation of the pan graph. Sometimes it is called the pan graph because it looks like a pan, like a cooking pan.
And so this is it was a little bit more difficult to prove. We again used our graphs G n of k, but it was much more complicated. And I could only do it for k equal to 2, 3, and 4, and the case equal to k equal to 4 was very complicated, so I didn't go any further. But we suspect that this would have a kernel for any k, that the token graphs on k tokens of this graph gen will always have a kernel. But it's just a suspicion. We basically don't know. Okay, so this is everything I wanted to talk to you about. Thank you very much for listening. If you stayed throughout the whole video, these are my emails. Feel free to email me any questions, comments, or if you just want to talk about graphs, just email me. Thank you very much.